Hello guys, welcome to Stat again. We are almost at the end and today we are going to start the new chapter, that is chapter number 9. Chapter number 9 is the 1 and 2 sample estimation problems. So let me just open the chapter and then after I will let you know that what exactly we are going to learn in this chapter. So 1 and 2 sample estimation problem. Look at here, guys. Here in this chapter, the purpose of this chapter is to build a foundation that allows us to draw conclusions about the population parameters from experimental data. Like example, the central limit theorem provides information about the distribution of the sample mean x bar. The distribution involves the population mean nu, and thus any conclusions concerning nu drawn from an observed sample average must depend on knowledge of the sampling distribution. And similar comments appear to S square and sigma square, right? So here in this chapter, what we are going to see, the purpose, we are going to see the purpose of statistical inference, how we are going to take care of the formally outlined purpose of statistical inference. We follow this by discussing the problem of estimation of population parameters. So estimation of population parameters. There are two types of estimation of population parameters. The first one is nothing but, you can see over here, there's a classical method, and second one is nothing but the Bayesian estimation or Bayesian method, you can say. We already went through the general philosophy of the formal statistical inference in chapter 1, and this statistical inference consists of those methods by which one makes the inference or inferences or the generalization about the population. And to distinguish between the classical method of estimation of a population parameter, whereby the inferences are based strictly on information obtained from a random sample selected from the population, and the Bayesian method, which utilizes prior subjective knowledge about the probability distribution of the unknown parameter in conjunction with the information provided by the sample data. So there are two methods. One is classical method, one is Bayesian method. Mainly we are going to see over here, we will rely on the classical method. Okay. And then after, the statistics inference may be divided into two major areas. One is estimation and one is test of hypothesis. Estimation, that's what we are going to see here in this chapter number 9. And the test of hypothesis, that's what we are going to see in the next chapter, that is chapter number 10. So let me just try to focus over here on the classical method of estimation. Before we start classical method of estimation, I just would like to provide you the general idea about what we are going to do in this chapter. So let me just stop this sharing this book and let me start sharing my whiteboard so that you will have clear-cut idea about this thing. So let me write something like this. Here I just would like to mention that chapter number 9, I think I can write something like this. Something like this. So this is my chapter number 9, and this is my chapter number 10. Chapter 9 is nothing but the estimation. Chapter 9 is the estimation, and chapter 10 is nothing but the test of hypothesis. Test of hypothesis. Okay, now estimation, that is divided into two categories. My first category is here, that is the one estimation. One estimation, and second one is two estimations. two estimations. In one estimations, we are going to see one estimation, that is article 9.1 to 9.5 in this book, in which we are going to see the variance. Variance means sigma square that is known to us, means it is given to us. Whenever the variance is known to us, this means that the standard deviation sigma is given, or you can say variance is given. Whenever standard deviation is given, we know this thing by chapter 8 that we are going to rely on the z-score. So we can do z alpha by 2. We can find z alpha by 2. Good. The another part of this one in which the variance is not given. Variance sigma square unknown. Variance sigma square. Here it is known, here it is unknown. Means standard deviation is not known to us. I'm talking about sample standard deviation. Sample standard deviation sigma not known, not given, you can say. Not given. And you know this thing that whenever this sigma is not given to us, at that time we rely on the chi-square distribution and we find the distribution, t alpha by 2. We are going to modify the same thing over here. Look at here, we are going to modify here when sigma is given. But suppose instead of 1, we have two estimations. What will happen for two estimations? That means instead of sigma, you have sigma 1 square and sigma 2 square. And both are known. Sigma 1 square and sigma 2 square, both are known. Because they are known, that means again we are going to rely on z-score, z alpha by 2. But there are two categories of sigma 1 and sigma 2 known. One is sigma 1 square is equal to sigma 2 square. Variance, both variance, they are known as well as same. Second one is sigma 1 square is not equal to sigma 2 square. Both are equally important, but make sure in both cases we are going to use z alpha by 2. Same here, suppose whenever we are given that this part is not known to us. So same way, suppose sigma 1 square and sigma 2 square, they are unknown. But again into two parts, unknown, it may possible, both are unknown, but both are same. Sigma 1 square equal to sigma 2 square. And they are not equal. Sigma 1 square equal to sigma. But because they are unknown, means we rely on chi-square distribution, or you can say t distribution, Here we have, I would say, if you want to draw the picture, you have something like this. Suppose you have z alpha by 2. This is my z alpha by 2. And z or negative of z alpha by 2, z of negative alpha by 2. And this is the region alpha by 2. This is the region alpha by 2. That means in this case, in both of this estimation part, we will be given, suppose we want to find the 95% of the accuracy, 99% of the accuracy, 98% of the accuracy, 90% of accuracy. This type of things would be answered using this estimation problem or using this chapter. Here we have, of course, as I told you, that T alpha by 2. So this is your T alpha by 2 and this is your alpha by 2. And here it is negative of T alpha by 2, or that is equal to T of negative of alpha by 2, you can say. And this is nothing but your alpha by 2. So that's what the outline of this chapter is designed. This is the outline of the chapter. And now we are going to start with the chapter 9, that is the estimation Or you can say in general, the 1 and 2 sample estimations. First of all, 1 sample estimation, and then after we will start accordingly the 2 sample estimations. Some of the things are given over here in the book, and that's why I just would like to continue with the same thing. Let me just save this file. Okay. And let me clear the picture so that I can go for something else. Okay. So now, first of all, let me let you know what we mean by the classical methods of estimation. And we are going to start with some of the fundamental things which are equally very useful to solve the examples. So let me just stop sharing this one and let me share my book so that we will have a little bit more clarification. A point estimate of some population parameter theta is a single valued theta cap of a statistic script theta cap. Okay, so theta cap, script theta cap is statistics, and the value, single value of that one, they are nothing but theta cap. So some population parameter theta is a single value theta cap in terms of statistics script theta cap. For example, the value x bar of the statistics x cap or x head computed from the sample size n is a point estimate of a population parameter nu. And similarly here, p cap is equal to x by n is a point estimation of a true population p for a binomial experiment. And as estimator is not expected to estimate the population parameter without error, yes, you will be having some error over here because the estimator is not expected. Whenever you go for the estimation, some estimation, that means you have most 99.99% you have some error. So estimator is not expected to estimate the population parameter without error. In both the cases, you're going to find some error. So we do not expect x bar to estimate nu exactly. So your mean exactly nu is not the exact value, but we certainly hope that it is not far off. That nu value is not far off the actual value. And for a particular sample, it is possible to obtain a close or closer estimate of nu by using the sample median x bar as an estimator. Sample median x bar as an estimator. And just keep in mind this thing that your mean equal to the parameter estimation, and estimator possessing this property that is said to be unbiased. So whenever we have what we mean by the unbiased estimator. So unbiased estimator, what are the desired properties of a good decision function that would influence us to choose one estimator rather than another? Let theta cap, script theta cap, your statistics, be an estimator value whose theta cap is a point estimator of some unknown population parameter theta, just like your, look at over here, the first line. Certainly, we would like to sampling distribution of script theta cap statistics to have mean equal to the parameter estimated. An estimator possessing these properties said the unbiased estimator. So I would say that definition of unbiased estimator is this one. A statistics theta cap is said to be an unbiased estimator if the parameter theta satisfies this estimator. Estimator in terms of statistics. Look at over here, theta. Don't forget this thing throughout this chapter that now onwards, this theta cap is the statistics and theta is the single value. Population parameter theta is a single value theta cap of the statistics script theta cap. So please keep this in mind. And now we are going to find the mu with respect to the statistics, and that's why we write mu theta cap or estimated value of theta cap, and that is equal to theta. And whatever I explained to you, I'm going to find ultimately the interval estimation. Interval estimation, here it is given that in terms of something. So first of all, I would just like to let you know that S square is unbiased estimator of the parameter sigma square. Means S square is unbiased estimator of a parameter sigma square. S square estimates sigma square, right? Just keep this in mind. That means S square is unbiased estimator of a sigma square. That means I'm going to prove that E is the estimator, capital E, of sigma square is nothing but S square. Is nothing but S square. And you can see over here, that's what is proved over here. Sigma ES square equal to sigma square. And that's not a big deal, but we have to just rely on our previous knowledge. I'm going to say chapter 8 or chapter 4, something like that. I think page number 2. Yeah, here we are on page number 267. Okay, fine. So let me again go back and I'm going to prove this thing. I'm going to explain to you what we mean by this one. And then after we will go for, you can see over here, although S square, here it is divided by n minus 1. We discussed this, why it is division by n minus 1, not by n. We discussed this thing in chapter 8. When time will come, I will let you know. This is the perfect time to make sure about the division by n minus 1, but not n. Although S square is the unbiased estimator of sigma square, on the other hand, it is usually a biased estimator of sigma, with the bias becoming insignificant for large sample. And this example illustrates why we divide by n minus 1 rather than n when the variance is estimated. When the variance, because you can see here you have n, here you have n. So you can have this n outside and n will get cancelled out. You can see that sigma x bar square equal to sigma square by n. This n and n gets cancelled out. And that's the reason that actually we are getting, I will let you know this thing that n and n gets cancelled out. And that's why we are getting n minus 1. So we divide by n minus 1. And then after we are going to discuss something about this definition too, that variance of a point estimator. So if we consider all possible unbiased estimator of some parameter theta, the one with the smallest variance is called the most efficient estimator of theta. The smallest variance. Smallest variance means it's high peak normal distribution, high peak. And low peak means large variance. So high peak. So if we consider all possible unbiased estimators of some parameter theta, the one with the smallest variance is called the most efficient estimator of theta. I will let you know this thing too. So first of all, let me start using this one. Let me stop sharing this one and let me start with my, again, whiteboard. So let's start with the whiteboard, and it says that the example 9.1, it looks very light. So let me use some red pen. Example 9.1, it says that so that S square is an unbiased estimator of the parameter sigma square. S square is the S square is the unbiased estimator of the parameter theta if nu of, as I told you, script theta head is equal to E script theta head, and that is equal to theta. That is actually the unbiased estimator definition, right? So unbiased statistics theta is said to be, I'm sorry, actually, let me just rewrite this one. It is statistics theta is unbiased. Let me write like this, statistic theta cap is unbiased estimator of the parameter theta if this condition is satisfied. If this condition is satisfied. And now I'm going to start my example 9.1. Example 9.1. And it says that S square is an unbiased estimator of a parameter sigma square. So that S square is an unbiased estimator of the parameter sigma square, full stop. Okay, so let me start with this one in on page number 244. If you recall this thing, last chapter, article 8.5, we went over, we showed one estimation, and that was, so article, I would say 8.5 page 244. If you refer this one, we proved one thing, that was summation I is equal to 1 to n xi bar, sorry, y. I is equal to summation I is equal to 1 to n xi minus xi bar whole square is equal to summation xi minus nu square minus n x bar minus nu square, if I'm not wrong. I is equal to, of course, 1 to n. I is equal to 1 to n. We proved this one. We have to show over here S square is an unbiased estimate of theta S square. That is, we are going to see that we are going to show that estimation of S square that is equal to sigma square. Right? That is to show this one. Okay, so let me start with estimation of S square, and that is equal to estimation of S square. Definition of S square is 1 over n minus 1, again the previous chapter, and summation of xi minus x bar square I is equal to 1 to n. I is equal to 1 to n, right? And I can plug this value of value from here. So that is equal to, I can write something like this. 1 over n minus 1 is constant. Let me pull it out. So 1 over n minus 1 big bracket. I am having over here summation of estimation of, right? So estimation of xi minus nu square minus n times x bar minus nu n square, and its estimation, because estimation is linear in addition and subtraction, and bracket complete. And of course, you know this thing, I don't have to write every time. I runs from 1 to n. And that is equal to 1 over n minus 1. And this is nothing but, yes, guys, what is this? This is nothing but your sigma xi square minus n times sigma x bar by definition. Why? Where I can write where the sigma xi square is nothing but sigma square for I is equal to 1, 2, 3 up to n, and sigma x bar square is nothing but sigma square divided by n, that is central limit theorem. So please keep this thing in mind. So that is equal to, I can write 1 over n minus 1 inside the bracket sigma xi square, that is equal to sigma square, and you have how many times? That is equal to I equal to 1, 2, 3 up to n, right? Actually sigma xi square, and you have to have summation I is equal to 1 to n, summation I equal to 1 to n. So that is actually n times, and here it is sigma square minus n, and sigma x bar is nothing but sigma square divided by n, and bracket complete. That is equal to 1 over n minus 1. If you take this n sigma square common, that means you're going to get, here it is 1 minus 1 over n. That is equal to, I can write 1 over n minus 1, here n sigma square out, and here you have LCM n minus 1 divided by n. Because this n minus 1 divided by n and n gets cancelled out, this n minus 1 and n minus 1 will get cancelled out. You're going to get sigma square. That means I have proved this thing, that estimation of S square is nothing but sigma square, or S square is unbiased estimator of the parameter sigma square. Now variance of a point estimator. So that's the proof. That's the proof. Of course, it is not required, but the proof goes like this. So guys, just keep this thing in mind, how it works. And now we are going to see, let me just save this file. And let me clear all my drawing, and let me start with the variance of a point estimator. So now let's see the variance of a point estimator. Suppose you have theta 1 cap and theta 2 cap. These are two, I would say, unbiased estimator of the sample population, two unbiased estimator of a sample population script theta. Two unbiased estimator of some sample population script theta. And if the sigma theta 1, whenever I write theta 1, it is the script theta, theta 1 cap square is less than sigma square and theta 2 cap, then this theta 1 cap is more efficient estimator of theta than theta 2. Theta 1 cap is more efficient estimator of theta than theta 2 cap. What does it mean? That means suppose you have some theta 1 cap, I would say something like this. This is my theta 1 cap. Sigma theta 1, there's a variance. If this variance is smaller than other variance, right? So suppose I have another variance, something like this. This is my theta 2 cap. You can see over here, this variance, this is my mean value. So this variance is, of course, this is my mean value somewhere over here. I have mean value. So this variance, you can see, this variance is smaller than the second variance with respect to the unbiased estimator theta 2 cap. Same way, suppose I have something like this. Like this, theta 3 cap, I would say, right? And this is nothing but my script theta cap. And this is nothing but my mean value, parameter theta. Right, guys? So that's what I mean by that theta 1, sigma theta 1 square here, sigma theta 1 square is less than sigma theta 2 and square, or sigma square theta 1 is less than sigma square theta 2, then sigma 1 is more efficient estimator of theta than theta 2. So please guys keep this thing in mind. And now we are going to start the next one. Okay. Clear drawing. And now let's start with the interval estimation. So what we mean by the interval estimation. So my next target is to find the interval estimation. Lots of things are given in the book. I don't think that you need to go through all of these things, but just pay attention over here. It is true that the estimation accuracy increases with large samples, but there is still no reason we should expect a point estimate from a given samples to be exactly equal to the population parameter it is supposed to estimate. There are many situations in which it is it's preferable to determine an interval within which we would expect to find the value of the parameter. Such an interval that is called the interval estimation. Such an interval that is called the interval estimation. I would say that suppose you have theta 1 cap, let me write like this. Suppose you have theta L cap is less than theta U cap. So what you mean by theta L cap? Theta L cap is in the lower confidence limit. This is nothing but the, let me change the color. So lower confidence limit, and this theta U is nothing but the upper, this L stands for this lower, U stands for this upper. So upper confidence limit. Right, guys? So this is, I would say, this is the endpoints of the interval. Other way around, I would say something like this, that endpoints of the intervals. If you are looking for the confidence interval, the lower interval and the upper interval, and this correspondingly, we are going to find the probability. So probability of theta L cap is less than theta U cap is always equal to 1 minus alpha, where 0 is less than alpha is less than 1, alpha lies always between 0 and 1, so that you have probability always between 0 and 1, always less than 1. Okay, one more thing, whenever you multiply this 1 minus alpha, this portion, by 100, so 1 minus alpha multiplied by 100, that means it is the percentage. That is called the confidence interval. Confidence interval. If this one, if you have the fraction 1, why fraction 1 minus alpha? Because alpha lies between 0 and 1. That's the reason. So fraction 1 minus alpha, that is called the confidence coefficient. Confidence coefficient, or you can say that as the degree of confidence. Degree of confidence. Right, guys? Degree of confidence. So that's what we are going to learn in this article. I just would like to explain to you a little more thing, how we are going to make use of our table A3 z-score and table A4, that is T distribution. So let me just save this file also, and I just would like to go for okay, and let me clear the drawing and let me start with this one. Suppose you have 95% of the confidence interval. Suppose you are looking for this one. Now, how it will work? Look at here, guys, 95%, that means actually it is 95% means 0.95. 0.95, you need to subtract from 1. So 1 minus 0.95, so that is equal to 0.05. This is your actually alpha value. We are looking for alpha by 2, so 0.05 divided by 2, so that is equal to 0.025. That is equal to 0.025. Here it is considered as something like this. This is my alpha by 2 and this is my alpha by 2. So that is nothing but, this area is nothing but 0.025. This area is nothing but 0.025. 0.025. Total area is nothing but 1. Total area is 1. And if you remove this one, this area is nothing but the 95%. Same way you can find 96%, 90%, 92%, 99%, whatever is asked to you. Good. Once I have this 0.95%, then what I'm going to do, that is 1 minus 0.025, and that is nothing but 0.975. And I'm looking for this 0.975 if we are given sigma or sigma x bar. If we are given this one, in that case, we are going to use Z table, Z score, Z alpha by 2. And that means we are going to take help of table A3. And we are going to find this value in the table because this is your area. This is your area. We are looking for this number. And if this corresponds to, suppose something like this, 0.095, that is equal to, I don't have, that is over here. But when we'll take the example, I will let you know this thing. So that is equal to 0.975, 0.975. And I can write that is equal to Z, but which alpha by 2? Alpha by 2 is 0.025. So Z 0.025, that is equal to 0.975, what it may be, using the table. So that's how you can find. Same way, suppose you have 99%, 99%, that is equal to 0.99. So 1 minus 0.99, that is equal to 0.01. And this is your alpha value. So if you divide by 2, 0.01 divided by 2, so 0.005. So this is my alpha by 2 value. And if you again draw the normal curve, you can see over here, 0.05. This is the region alpha by 2. 0.005, and this is the region, and this is 99%. This is your alpha by 2, 99%. So once you have this one, so 1 minus 0.005, and that is equal to 0.995, right? 0.995. And if you look at this value in the table, whatever the value you're going to get, that is equal to Z alpha by 2, 0.005, that is equal to that value over here. So that's how you can use your G distribution table. So always, guys, please keep this thing in mind. And now we are going to see, the single sample estimation of the mean. Single sample estimation of the mean. Now, please keep the, I just would like to show you the book just for a second or like this, but most of the things we are going to write it down over here. Okay. Let me clear the drawing, and now let me stop sharing this whiteboard. Let me go for a book. Let me share my book. And you can see over here, we finished this part, we did this thing, we did all these things. This is what I explained to you. Everything is mentioned here. Just read this part. And right now we are doing this thing, single estimation, single sample, that is the estimation to the mean. Single sample, estimation to the mean. So what we mean by this one, please keep this thing in mind that always we're going to get that sigma s square, sigma square x bar equal to sigma square by n, central limit theorem, because sigma is known to us. And that's what we are going to use over here. So please keep this thing in mind, and let me start with this one. So the sample distribution of x bar is centered at nu. And the most application, the variance is smaller than that of any other estimation of nu. Thus, the sample mean x bar will be used as a point estimator or as point estimate for the population mean nu. Keep in mind this thing, the sample mean x bar will be used as a x bar, right? Will be used as a point estimate, mean statistics for the population mean nu. And recall that central limit theorem, sigma x bar square equal to sigma square by n for a large sample yield the value x bar that comes from the sampling distribution, that comes from the sampling distribution, very important thing, that comes from the sampling distribution with a smaller variance sampling distribution. And hence x bar is likely to be very accurate estimate of nu when n is large. X bar is very accurate estimation. X bar is likely to be very accurate estimation of nu when n is large enough. Okay, guys. And according to the central limit theorem, we can expect the sampling distribution of x bar to be approximately normally distributed with mean nu x bar equal to nu. Nu remains the same. Mean remains the same. Nu x bar equal to nu. Look at here. Nu x bar equal to nu. Okay. And that's why how this works. Just look at over here, because we are going to use the same theme throughout this chapter. So let me again stop sharing this one, and I will let you know this thing using my whiteboard. So it says that if you have, suppose, as I told you that sigma x bar square, that is equal to sigma divided by square root of n. Sigma divided by square root of n. That is actually no square, right? Otherwise you can say no square. Yeah. Always we take the positive square root. So my probability, what is my probability? My probability of negative z alpha by 2 is less than z positive z alpha by 2 equal to 1 minus alpha. And you know this, what is my z? Z is nothing but x bar minus nu divided by sigma over square root of n, right? Sigma known. If I plug this value over here, just plug this value of sigma over here, I'm going to get probability of negative z over alpha is less than x bar minus nu divided by sigma square root of n, then that is less than z alpha by 2, and that is equal to 1 minus alpha. That is equal to 1 minus alpha. Good. What does it mean? That means again, it is the same thing that you have here, alpha by 2, this is your region, alpha by 2, this is your region, alpha by 2, and this part is 1 minus alpha, because alpha by 2 is alpha, and one total probability is 1, so 1 minus alpha, and your mean is 0, because z score means your mean is always 0. Okay, how it will work? That means I'm looking for this value. I'm looking for this mean, new part, new value. That means let me divide both the sides. Oh, sorry, let me multiply both the sides by sigma, just simple algebraic calculation. So I can write negative z alpha by 2, right? Actually, z alpha by 2. Let me rewrite this one. Okay. So negative z alpha by 2. This is the right way of writing. So z alpha by 2 times sigma over square root of n is less than x bar minus nu is less than z alpha by 2 and sigma over square root of n, and that is equal to 1 minus alpha. Okay, guys. And this implies that I want this nu, as I told you. So let me just subtract x bar throughout. So probability of negative of x bar minus z alpha by 2 and sigma over square root of n is less than negative of nu, and that is less than negative of x plus z alpha by 2 and sigma over square root of n, and that is equal to 1 minus alpha. That is equal to 1 minus alpha. Okay, guys. Now I want here positive sign because I want nu. So let me just multiply throughout by negative signs. If you multiply throughout by negative sign, this inequality, you're going to get x plus z alpha by 2 and sigma over square root of n. Because we are multiplying with negative sign, this less than will be converted to greater than. This is greater than, and here it is x minus z alpha by 2 and sigma over square root of n, and that is equal to 1 minus alpha. And this implies that I can write probability of, let me write in a less than form. So I can write that is equal to x minus z alpha by 2 and x minus z alpha by 2 and sigma over square root of n is less than nu is less than x plus z alpha by 2 and sigma over square root of n, and that is equal to 1 minus alpha. That is equal to 1 minus alpha. So that's what we mean by this is the random sample of size n is selected from a population whose variance sigma square is known. So again, I told you that sigma square is known. Sigma square is known. And confidence interval, this is the interval. This is the interval. This is called the confidence interval. And this confidence interval, this is called the whole portion that is called the confidence interval, because your nu lies between these two. So that's why it is called the confidence interval. The z alpha by 2 here, that is nothing but z alpha by living on the area of alpha by 2 to the right. So I can mention a little bit over here that z alpha by 2 is the z value. Let me write living an area of alpha by 2 to the right. The small shape selected from the normal population, we cannot expect our degree of confidence to be accurate. And however, for the sample size n greater than or equal to 30 as usual, just like the previous chapter, right? N greater than or equal to 30, with the shape of the distribution not too skewed, not very much right skewed or left skewed, not too skewed, sampling theory guarantees good result. And clearly, whatever I have, if you compare this one with my previous slide, so this part is nothing but this one. Let me change the color. Maybe you will have some better flavor. Oops. So this part is nothing but your script theta L head is less than nu is less than script theta u head. This is my script theta head u and theta head L. So lower limit and upper limit. The larger of the value, the larger the value we choose for z alpha by 2. This z alpha by 2. The larger the value we choose for these two, z alpha by 2. The wider we make all the intervals, and the more confident we can be that the particular sample selected with which will produce an interval that contains an unknown parameter nu, right? So larger the value of Z alpha by 2, wider we make all the intervals, and the more confident we can be that the particular sample selected with production or with produced an interval. Okay, let's go for the example. Now my example is something like this, guys. If I go for, okay, let me just save this file. And now let me go for just clear. Let me stop sharing this one and let's go for the book again. So I explained to you how this comes over here. I explained all this portion to you, this one, all these things are done. And now we start the example slowly. Okay, guys, just keep this thing in mind and read the example twice. And then after I will let you know how to get the solution of the example. Okay, so my solution is something like this. Example is like this. The average zinc concentration recovered from a sample of measurements taken in 36 different locations in a river is found to be 2.6 grams per milliliter. Find the 95% and 99% confidence intervals for the mean zinc concentration in the river. So we are asked two questions. One is 95%, second is 99%. These are the main two standard confidence intervals type, 95% and 99%. But it could be 93, 90, something like this too, 98. Assume that the population standard deviation is 0.3 gram per milliliter. This standard deviation means variance, sigma. Standard deviation is sigma. So sigma square is 0.3 square. So that is given to us. Please keep this thing in mind. So again, read this example. You are given that the measurements taken in 36 different locations means your n equal to 36. Right, guys? And then after 2.6 milligrams per in rivers is found, 2.6 grams per milliliter. Okay, standard deviation, mean value, everything is provided to us. So this mean is nothing but actually X bar. This 2.6, that is nothing but my X bar. So please keep this thing in mind. That is my X bar. And we are looking for this new value in which interval new is lying. 95% interval we want to find, and we want to cover 99%, and we want to find the interval. Naturally, 99% would be, which one would be better? Yeah, we will decide this thing, right? 95 and 99. So naturally, 99 will give you larger domain, larger interval. We will see that thing. Okay, so just keep this thing in mind and let me start with this example. So let me, again, how I can go for this one, I will let you know everything. It is very easy. Just stop sharing this one and let me go for, again, the whiteboard. And my example says something like this. My example says something like this. It says example, okay, let me just finish or let me clear. The board, okay. Example number 9.2. The 9.2 says that, okay, so first of all, as I told you, my X bar is nothing but 2.6. X bar is 2.6. The Z value living an area, okay, we have 95%. First of all, 95%. So I would say A part and B part. A part and B part. This X bar remains the same. X bar is equal to 2.6, and here it is 95%. Here it is 99%. 95% means you have that is equal to 0.95. So this implies that 1 minus 0.95, that is equal to 0.05, and that is my value of alpha. So alpha by 2 is equal to 0.05 divided by 2, so 0.025. 0.025. And again, let me draw the picture for you guys. So this is my alpha by 2. This region is alpha by 2. This region is alpha by 2. So alpha by 2 is equal to 0.025. And this is 0.025, right? And this is my 95% of the interval. Okay. 95%. So what we mean by this one? So 0.07, so 1 minus 0.025, that is equal to 0.975. So this region is nothing but 0.975. And if you find this 0.975 on your table A3, let me just show it to you. So you're going to get that is equal to 1.96. I will just show this one once to you. Thereafter, you can figure it out. So here it is, that is equal to 1.96. Let me just save this one. And then after, let me stop sharing this one and let me share my book. This is the, it's very time consuming. We are on the page number 271, okay? And you are given the table on page number 736. Okay, so let me just take it over here. 736. Right? 735 and 736. You can see over here, my value was 0.975. If you try to figure it out, the value 0.975, it will be somewhere, it's not over here, but the backside 0.975, 0.975, 0.979797 and 9750. Look at over here, and that corresponds to 1.9 over here. Look at here, 0.975, 1.9 over here, and here it is 0.6, so 1.96. Right, so that's how you can figure it out. 1.96. Just keep in mind this thing, 95 will always give you 1.96, and same way you have 99. So 99 means it is 1 minus 1 minus something you are going to get for 99, 1.005, right? So 1.005, 1 minus 1.005, that is equal to 1 minus, I will let you know how I'm calculating these things. So it is 1.995. So 995 will be somewhere over here. 995 is 1.995. So one value is fixed now. For 95%, it is 1.96. And for 99%, your z-score value will be 9975 0.00, so 0.9995, right? So it is 2.99. Okay, so 2 points. See here, guys. 5 and here it is 7. So here it is 7, 2.5, 2.5 and 7.9950 between this one, 9949 and 9950 or 51. So somewhere over here. So it is here. So it is 2.5 and this is 7 and 8, so 575. That's the fixed value. Always keep this thing in mind. Okay, and now I will let you know how we are taking care of this part. Okay, first of all, let me go back to my book page. So my book page was 273. 273, right? Okay, so let me stop sharing this one. And again, let me go back to my whiteboard. We have the whiteboard over here. And now let me, this is really very light. So now 0.975, as I told you that 0.975 is nothing but your Z alpha by 2. What is Z alpha by 2? That is equal to Z alpha by 2. Z alpha by 2 is 0.025. Don't write this one. We have found this value in the table, and corresponding value was 1.96. 1.96. So my Z alpha by 2 is 1.96. Okay, same way here. That is equal to 0.99. So 1 minus 0.99, that is equal to 0.01, and that is my alpha value. So alpha by 2 is equal to 0.01 by 2, so 0.005, and 0.005 means exactly same over here, but very small interval, very small space. This is my alpha by 2, and this is my alpha by 2, 0.005, and this is my 99%. And this 0.1 minus 0.005, that is equal to nothing but 0.995, and that's what we figured it out, right? 0.9950 and 0.99995, and this value corresponds to, so z alpha by 2, that is equal to z 0.005, that corresponds to, we just figured it out, that was 2 point did I write anywhere? It is 2.575. 2.575. So that's how you can find this z-score. And now let me plug this value in my formula. What was the formula? The formula was, I don't have enough space here, but formula was x bar is equal, x bar minus z alpha by 2. And just now we proved this formula in the previous slide, and that is less than nu, and that is less than x bar, this is x bar plus z alpha by 2 and sigma over square root of n, when we are working with simple one estimate, one sample, and sigma known. So just plug the values. If you plug the value over here, you're going to get x bar is nothing but your 2.6, so 2.6 minus z alpha by 2 is nothing but your z alpha by 2, 1.96, so 1.96. So minus 1.9 sigma is given to you. What is your sigma value? Sigma value, that is nothing but it is 0.3 in this example. So sigma is equal to 0.3, right? And you are given n equal to 36. Okay, so sigma equal to 0.3. So I can write 0.3 and square root of 36 means 6 is less than nu is less than 2.6 plus 1.96 and 0.3 divided by square root of 36. Use your calculator and you're going to get one number over here on the left side. So that number will be 2.50 is less than nu is less than this number is 2.70. So that means your interval will be 2.50 to 2.70. That is your confidence interval. That is your confidence interval. Same way you can find the confidence interval over here using the same format, same formula. So let me just plug the values here. I got 2.575 minus 1. No, my bad. Let me just use the eraser, and it says that same formula, and it says that x bar is 2.6 remains the same minus z alpha by 2. Z alpha by 2 in this case is 2.575. 0.3 will remain the same, and here it is square root of n is 36 is 6, less than nu is less than 2.6 again will remain the same, plus 1.9, my bad, plus 2.575 and 0.3 divided by 6. So if you use your calculator here, you're going to get that is equal to 2.47 is less than nu, and that is less than 2.73, because you have a little bit more region over here, 99%, and that's why. And this area actually is nothing but 0.99995, this one, and that's why you have this one. And that because it is larger area, this interval, confidence interval, must be larger than the previous one. So this is the confidence interval. Confidence interval. So this way, guys, you can solve the examples. One more definition is there, and that is called, let me just save this file and let me go for the next one. Okay. If x bar is used as an estimator of nu, this is in the form of theorem 9.1. If x bar is used as an estimator of nu, we can be 1 minus alpha percentage confident. So we can be 100 times 1 minus alpha percentage confident that the error will not exceed, that you know this z alpha by 2 sigma over square root of n. So we had this portion both sides. So this is actually called error estimation. So I would like to write equal to this one. Sometimes people are writing the corollary of theorem 9.1 in the form of, I would say again, theorem 9.2. That's fine. 9.2, if x bar is used as an estimator nu, same thing. If x bar is used as an estimator, nu, we can be again 100 times 1 minus alpha percentage confident that the error will not exceed the specific amount of E. Error will not exceed a specific amount E when the sample size is. So if you are asked to find the sample size, when a sample size is, so you can write this is something like this. See, out of this equation, you can make, look at over here, let me just change the color. You can make from, look at here. Let me write z alpha by 2 and sigma is equal to E times square root of n. And this implies that I can divide by now E. So z alpha by 2 and sigma divided by E, that is equal to square root of n. And what is this? That means if you write, if you want to write n, so n is nothing but, and that n comes over here. So n is equal to, take the square both sides. So z alpha by 2 sigma divided by E and whole square. So that's how you can find the sample size. Suppose sometimes sample size is not given to us, then you want to make sure what is your sample size, if it is greater than 30 or less than 30, what it may be. So please make sure about this thing. So when solving for the sample size n, we round all fractional values up to the next whole number, because sample size could not be 1.5, right? Either it is one sample or two sample or three samples like this. So please make sure that when you find sample size, and suppose you are getting 1.7, we are going to round that figure to 2. 1.2, we are going to round that figure to 1. Something like this. Always you have to round in terms of the natural number or whole number. And by adhering to this principle, we can be sure that our degree of confidence never falls below 100 times that 100 times 1 minus alpha. 100 times 1 minus alpha percentage. And strictly speaking, the formula given over here in this theorem, n, that is applicable only if we know sigma square, the variance of the population. Okay, in all the cases, sigma is known. Sigma is known. I've started with this, with the known sigma, from which we select our sample. And lacking this information, we could take a preliminary sample size. If that is not known, in that case, we could take the preliminary sample size and greater than or equal to 30 to provide an estimation, an estimate of sigma, right? If sigma is known, then it's fine. If not, then we have to make sure that for n greater than or equal to 30, right, we could take the preliminary samples of size n greater than or equal to 30 to provide an estimate sigma. Okay, guys, I would like to give you one example over here. As per example, suppose example based on this theorem. How large a sample is required if we want to be 95% confidence that our estimate of new in previous example, right? 9.2 is off by less than 0.05. It says that how large a sample size, how large sample size it is required if we are looking for 95% of the confidence interval. Confidence interval that of new. Estimate of new, where I was, I'm sorry. So is required. So that means we can go for n greater than or equal to 30, provide an estimation of sigma, right? Then using S as an approximate for sigma, in our previous theorem 9.2, this theorem 9.2, we could determine approximately how many observations are needed to provide the desired degree of accuracy. Okay, guys. So here let me write for 95%. You know this thing that my n is equal to z alpha by 2. Z alpha by 2, we figured out that was 1.96. If you look at the previous slide, and then after my sigma was given to us, that was 0.3. And then after this, my error E, this is my error E, right? So error E, that was, it is given less than 0.05. That means this is the value, this is my error E. So that is equal to 0.05. And I have to make a square of this one. So if you use your calculator, you're going to get 138.3. So approximately, I have to round this number. So I'm going to say that 138, right? So 138. So therefore, we can be 95% confident that the random sample size of 138, or you can say, well, right, 139, I don't mind. 139 will provide an estimate X bar differing from nu by the amount less than 0.05. That is the meaning. I repeat, this 138 or 139. So 95% of the confident, we can be 95% confident. I repeat, we can be 95% confident that a random sample size of 139 will provide an estimate X bar differing from nu. X bar differing from by an amount less than 0.05. That is the meaning. By amount less than 0.05. Okay, guys. Now I just gave you two-sided interval, right? But sometimes it is required in the practical purpose that we just want one-sided confidence bound, not two-sided, but one-sided confidence bound. The one-sided confidence bound can be written in the form of, let me again save this file. Most of the things we are, whatever we are doing today, that is based on the whiteboard. Okay. So one-sided confidence bound. One-sided confidence bounds, right? The confidence interval and the resulting confidence bound discussed thus so far was two-sided. However, there are many applications in which only one side is required, one bound is sought. For example, if the measurement of interest is tensile strength, the engineer receives better information from a lower bound only. He doesn't want the upper bound because measurement tensile strength means just the lower bound is required, right? The engineer, I would say, if the measurements of the interest is tensile strength, right? How much strength is there? So in that case, the engineer receives better information from the lower bound only. And this bound communicates the worst case scenario. On the other hand, if the measurement is something for which relatively large value of nu is not profitable or desirable, relatively large value of nu is not profitable or desirable, in that case, only upper bound is required, right? Because once we cross that value, that means company will be at loss. So the measurement is something for which a relatively large value of nu is not profitable or desirable. In that case, we are looking for only the upper bound. So one can minimize the cost also for the based on the calculation, because once you write the code program, MATLAB code or something like that, so one can reduce the cost save the time like this. Okay, using central limit theorem, we have probability of x bar, or I would say like this, probability of z is less than z alpha, and that is equal to z is nothing but x bar minus nu over sigma square root of n. Central limit theorem, you know this thing, central limit theorem, and that is less than z alpha. That is less than z alpha, and that is nothing but 1 minus alpha. That is equal to 1 minus alpha. So again, you are looking for this nu, just like the previous calculation. You can do something like this. Just multiply this 1 by sigma alpha, take this one over here, and then subtract or add negative x throughout, and then change the sign, and then nu. So you're going to get that is equal to, because nu is there, so nu is greater than x bar minus z alpha by 2 and sigma over square root of n, that is equal to 1 minus alpha. This is called the upper bound. This is called the upper bound. And the same way, similarly, if we have, suppose, like this, p z alpha is, or I would say z is greater than negative z alpha, right? Z is greater than negative z alpha. So probability of x bar minus nu over sigma over square root of n, that is, sorry, sigma over square root of n, oh my gosh, that is greater than negative of z alpha, and that is equal to, keep this one to other side, and you're going to get probability of nu is less than, and of course that is equal to 1 minus alpha, 1 minus alpha, that is equal to probability of nu less than x bar plus, yes please, z alpha by 2 and sigma over square root of n, that is equal to 1 minus alpha. That is equal to 1 minus alpha. This implies that, right? And this is called the this is called the upper bound. This one is your upper bound greater than. This one is your lower bound because less than, right? So this is the upper and lower bound. So upper bound, that means with plus sign, just keep in mind this thing. Lower bound means it is negative sign. Upper bound and lower bound for sigma square known. Just again keep in mind this thing, sigma square is known, right? And nu is of course known. Nu is known too. Sigma square is known and nu is known to us. Now, there are some examples you can use for this one. And example 9.4, that is exactly same as this one. If you want to find just one upper bound, you can use this one. That's not a big deal. So I think let me just go for the next part, or I can read this example very quickly for you, that if a psychological testing experiment, 25 subjects are selected randomly and there's reaction time in seconds to a particular stimulus is measured. Past experience suggests that the variance in the reaction time to this type of stimuli is 4 seconds square, and the distribution of the reaction time is approximately normal. Okay, the average time for the subject is 6.2 second. 6.2, that is your x bar. So x bar that is equal to 6.2 second is given to you, and you are given 25 subjects, means n is equal to 25, and you are given how much? 4 seconds. That is the past experience suggests that the variance in the reaction times to this type of stimuli is 4 seconds. So variance that is equal to sigma square, sigma is equal to 4 seconds square. 4 seconds square. Right, guys? Okay. And then after we want to find, the question is give the upper 95% bound. Upper 95% bound. Upper 95% of bound, or you can say Q or find upper 95% of bound. Again, guys, exactly same thing, 95% of bound. Look at over here, it is something like this. Here it is 95%, so that is equal to 0.95. So 1 minus 0.95, that is equal to 0.05. 0.05, and that is your alpha. So That is my alpha, 0.05. Now don't do, this is just your upper bound. We are not doing anything over here. So this is your just alpha. So don't do anything over here because as you know, I did not write any alpha by 2. It's simply alpha here. It's simply alpha. So we have to work with this alpha. So this region is 0.05. And because I want the upper bound, this value 1 minus 0.05, that is equal to 1 minus 0. This is 1 minute. Yeah, so that is equal to 1 minus 0.05, that is equal to 0.95 or 950, and that corresponds to, if you look at the table, you're going to get 1.645 in that z-score table. You can find that is equal to 1.6 on the vertical line, and the horizontal line, it was on 0.045, 0.4 and 0.5 in between. So that means I can write that is equal to, upper bound is x bar plus z alpha and sigma square root of n, that is equal to 6.2 plus 1.645, and sigma 25, that is equal to 6.2 plus 0.658. If you add this one, 6.858 seconds. 858 seconds, right? So 95% of confidence interval, that mean that the mean reaction time is less than 0. I think it is 6.858 seconds. 6.858 seconds. 95%. We are 95% confident that the mean reaction time. So 95%. We are 95% confident. So we are 95% confident that mean reaction time is now upper bound. Upper bound means this mean reaction time will not exceed this one, right? This 6.858. So mean reaction time will not exceed this part, right? So 95% we are confident that mean reaction time will not exceed. Mean reaction time is less than 6.858 seconds. So that's how you can use the upper and lower bound. Again, guys, that is simple. Let me save my file. And now I just would like to go for the second part in which the case of sigma unknown. What will happen when sigma is unknown? Okay, guys, now unknown sigma. Sigma is unknown. Please keep this thing in mind. Sigma unknown. What will happen when sigma is unknown? As you know that when sigma is unknown means value of sigma, the variance is not given to us. In that case, we rely always on degree of freedom and your t distribution, and t distribution that is given in terms of x bar minus nu divided by s over square root of n, right? So we saw this thing in the last chapter that if we have a random sample from a normal distribution, then the random variable t has a standard t distribution, has a standard t distribution with degree of freedom v is equal to n minus 1. You know this thing. And s is the sample standard deviation. This s is nothing but the sample standard deviation, right? It's just the sample standard deviation. And in this situation, sigma is unknown and t can be used to construct the confidence interval nu. Exactly same thing, guys. If you look at, just allow me to work like my previous case. So probability of, but not z, negative of t alpha by 2 is less than capital T is less than t alpha by 2, and that won't exceed 1 minus, that is equal to 1 minus alpha. Let me plug the value of this t. So negative of t alpha by 2 is less than x bar minus nu divided by s square root of n, and that is less than t alpha by 2, and that is equal to 1 minus alpha. And again, I'm looking for this nu. So let me multiply throughout by, this is negative of t alpha by 2, and s over square root of n is less than x bar minus nu is less than I would say T alpha by 2 and S over square root of N, and that is equal to 1 minus alpha. If you want to negative X bar, if you want to add this one, so negative X bar and this will get cancelled out, and here you're going to get negative X bar and plus this one. Now I want to remove this negative signs, multiply throughout by negative signs, so I'm going to get that is equal to P. So X bar plus T alpha by 2 and S over square root of N is less than, not less than, actually it is greater than. So is greater than nu is greater than X bar minus T alpha by 2 and S over square root of N, right? Exactly same thing, just I replaced Z by T. That's it. And I would like to write this term first. So I'm going to say that P and X bar minus T alpha by 2 S over square root of N is less than nu is less than X bar plus T alpha by 2 and S over square root of N, and that is equal to 1 minus alpha. And you can see over here, guys, whatever I explained to you, that was exactly same as I told you last time. So here is your mean 0 because T distribution and Z distribution gives you mean 0. This is your alpha and alpha. This is your alpha by 2. This one is nothing but your alpha by 2, both sided. And that's why I can say this region is nothing but 1 minus alpha because total is 1, right? And the confidence interval when sigma square is unknown, that is given by this one. This is the confidence interval that is given by this one, right? The confidence interval is given in this form. Okay, and computed one-sided confidence interval for nu with sigma unknown are just same as one can expect the same thing, X bar T alpha by 2, or sorry, T alpha. So one-sided interval, I don't want to prove this thing again, but exactly same thing we can refer, or let me say like this. We have made a distribution between the cases of sigma known and sigma unknown in computing confidence interval estimation. We should emphasize that for sigma known, we exploited the central limit theorem. Of course, you know this thing. Whereas for sigma unknown, we made use of the sampling distribution for the random variable T. Sampling distribution for the random variable T. You know this thing. Sampling distribution for the random variable T, right? Good. So if you want to compute the upper and lower limit in terms of T, you're going to get the upper limit is nothing but that is equal to X bar plus T alpha, not alpha by 2, you know this thing because we are counting just one-sided, and X by N. Another is X bar minus T alpha and X over square root of N. And they are the upper limit, upper and lower limit. This is the upper limit and this is the lower limit. See, upper and lower limit or 100 times 1 minus alpha percentage bound respectively. And T alpha is a T value having the area of alpha to the right, right? This T alpha is nothing but the T value having an area of course, alpha to the right. Because we have, in this case, we have just one-sided. So this is my alpha. Okay, guys, let me save this part. And now I would like to start with the examples. So one more example, 9.5. And then after we are going to see one more thing, that is the again, the same thing. Often statisticians recommended that even when normality cannot be assumed, if it is not normal, again, sigma is unknown and N greater than or equal to 30, S can be replaced by sigma. S can be replaced by sigma and the confidence interval can be found, right? Exactly same thing, guys. So please keep this thing in mind too. And now standard error for the also we can find the error estimation. So I would like to take that error estimation and then we can solve the example. Just like my previous section, I can find the error estimation over here. As I told you that X bar plus Z alpha by 2 sigma over, I think you already got it. So X bar plus or minus T alpha by 2 S over square root of N. that is the confidence limits on nu and sigma square unknown. X bar, let me just save this one, and yeah, so X bar plus or minus T alpha by 2, this one, X bar minus and plus, so plus or minus T alpha by 2 S over N, right? That is equal to X bar plus or minus T alpha by 2 and standard error of X bar. So this is your standard error, T alpha by 2 and the standard error. Estimate standard error. You can say estimated standard error, or you can say standard error. Estimated standard error. This one. Estimated standard error of X bar. Okay. So now, guys, I think the time has come to go for the practical, I mean to say exercise problems, and then after, I think it's a very long video. So once we are done with some of the exercise problems, I just would like to stop over here. And next time we are going to see the two samples estimating the difference between two means. Two samples and estimating difference between two means, article 9.8 and 9.8. And I think, yeah, that's it. So 9.8, that's the only article we are going to see next time. But it's a lengthy article, so it will again take some time. But we'll figure it out. And that is the end of this chapter. And then after we're going to start the new chapter. So let me just continue with few examples over here. Let me just save this one in the folder. And let me clear my drawing, clear the drawing. And now let's go for the example. Let me stop sharing this book. I'm going to say slide, and let's start with the book. All these things we already figured it out. So now let me just go through. We did all these things, and now we are going to start the exercise problems. Okay. Look at here, guys. If I want to go for the first problem, my first problem says something like this. Now you know how to see the values. Use the score table and the Z table A3 and normal distribution. If sigma is known, sigma is not known, then T distribution, you know this thing. Let me read this example for you. A UCLA researcher claims that the lifespan of mice can be extended by as much as 25% when the calories in their diet are reduced by approximately 40%. Right? Lifespan can be expanded by as much as 25% when the calories in their calories in the diet are reduced by approximately 40% from the time they are given, they are weaned. Okay. The restricted diet is enriched to normal levels by vitamins and the proteins, assuming that it is known from the previous studies that sigma equal to 5.8 months given to us. How many mice should be included? How many mice means number of samples. N is asked to you. So we have to use that formula, N equal to Z alpha by 2 sigma divided by error square. Okay. So we need to find Z alpha by 2 because we are given 99% of the confidence interval. So based on this, we can find Z alpha by 2. How many mice should be included in our sample if we wish to be 99% confidence that the mean lifespan of the sample will be within 2 months of the population mean for all mice subjects to this reduced diet? Okay, not a big deal. Very simple example. So again, guys, look at here. Example 9.1. Exercise 9.1. So it says that my sigma is equal to 5.8. My error is nothing but 2 months. So error is equal to 2. So I can write N is equal to, oh, sorry, I have to first find, okay, Z alpha by 2 and sigma divided by R divided by E, right? Divided by E and square. but I need to find first Z alpha by 2. So where I can say that Z alpha by 2, that is 99%. You know this thing, 99% means that is equal to 0.99. So 1 minus 0.99, that is equal to 0.01. And that is my alpha. So alpha by 2 is equal to 0.01 divided by 2, 0.005. So if you draw the picture, you're going to get that is equal to, this is my alpha and this is my alpha by 2, and alpha by 2, that is equal to 0.005, right? And this is 0.99. Okay, so 1 minus 0.005, that is equal to 0.995. And if you find this value in your table A3, if you use your table A3, you're going to get that is equal to, that corresponds to the corresponding value is nothing but 2.575. You already figure it out. So I would say that Z alpha by 2 is equal to Z 0.005. That is equal, right? Always Z value. That is equal to 2.575. So plug this value here, 2.575, and sigma is given to you 5.8 divided by E is given to you 2, and make square and just use your calculator. I have the answer here, it is 56. Or if it is not 56, in that case, you can 56.2 or like this, you can round the number, you know this thing. So please round to whole number. Round to whole number, please. So that is my example 9.1. I would like to go for my next example, that is 9.2. Let me read that example now. Let me stop sharing and let's go for the book again. So 9.2 says that an electrical firm manufacturer light bulbs that have a length of life that is approximately normally distributed with a standard deviation of 40 hours. If a sample of 30 bulbs has a given life of 780 hours, see normally distribution with the standard deviation 40 hours, sigma equal to 40 given to us. If a sample of 30 bulbs n equal to 30 is given to us, the average life of 780 hours mean value is given to us, means X bar in terms of samples, right? So X bar is given to us, find 96% of the confidence interval for the population mean. So now we have to find for 96%, that's the only difference. So it's really very simple. Let me just go for this one. So again, let me share my whiteboard and I can go for 9.2. Okay, so 9.2 says that I have n is equal to, I have n is equal to 30, X bar is equal to 780, and then sigma is equal to 40. Sigma is equal to 40 given to us. And we are given 96%, that is equal to 0.96, that is equal to 0.96. This is 1 minus 0.96, that is equal to, I can write 0.04, and that is my alpha. So alpha by 2, that is equal to 0.02. Right, guys? So 1 minus 0.02, that is equal to, yes, please, that is equal to 0.98. That is equal to 0.98. If you find this 0.98 in your table A3, this value you can find in the table, and that corresponds to this 0.933, that corresponds to 2.0 and between 2.0 and 5.4. So 2.05, and you can say between 5 and 6, you can write 4 or 5, whatever you want to say, 2.05. And thereafter you can plug this value in the formula. Formula is X bar minus, you know this thing, Z alpha by 2, and then sigma over square root of n. Square root of n minus nu is less than X bar plus Z alpha by 2 and sigma over square root of n. If you use this one, I think it's very light. So let me use some dark color. Okay, if you plug the value over here, you're going to get that is equal to 780 minus 2.055 2.055, and here it is 40 divided by square root of 30 minus is less than nu is less than 780 plus 2.055 and 40 divided by square root of 30. So if you use your calculator, you're going to get 765 is less than nu is less than 795, right? Is less than 795. So this is the 96%. So 96%. So we are 96% percentage confidence interval for the population mean of all light bulbs produced by the firm. We are 96% confident that the all light bulbs produced by the firm has average life of 780 hours. 96% confident that the light bulbs produced by a firm has an average life of 780 hours. So make sure, guys, whenever you have this type of example, you are writing this thing in terms of the question in which form it is asked, right? So let me just save this one. And now let me clear the drawing, clear all drawings. And now let me go for my next example by sharing my book. So let me share my book, and my book is over here. Yes, I'm getting tired. It's almost 2 hours. Okay, my next example, that is example number, I would say I can go for, number of examples are there. Let me just go for 2 examples and we are done. Let me go for example 9.4 and 9.5. 9.5 that is attached with 9.15 also. So let me go for this one, 9.4. So 9.4 says something like this. 9.4, then 9.5 with 9.15. So that sounds good. 9.4 and 9.15, I'm going to, 9.4 first we are going to finish. The heights of our random sample of 50 college students showed a mean of 174.5 centimeters and the standard deviation 6.9 centimeter, right? Mean and standard deviation are provided to us. Construct 98% of the confidence interval for the mean height of college students. And what can we assert with 98% of confidence about the possible size of our error if we estimate the mean height of all college students to be 174.5 centimeters, right? So we are answering these 2 questions. Just read this thing twice so that we can start. Second part is based on the error estimation. So our error will not exceed something, right? It says that if we estimate the mean height of all college students be one set estimation, our error if, about the possible size of our error, right? It should not be less than, error should not be less than some numbers. Okay, so let me start with this one, guys. So let's start with example 9.4. 9.4 says that exercise 9.4 says that I have n is equal to 50, x bar is equal to 174.5, sigma is equal to 6.9 given to us, and we are given 98% of the confidence of 0.98, that is equal to, so 1 minus 0.98, that is equal to 0.02, and that is my alpha value. So if you divide by 2, you're going to get that is equal to 0.01, and 1 minus 0.01, that is nothing but 0.1, so that is equal to 0.99. 1 minus 0.01, that is equal to 0.99. So z value of 0.01 alpha by 2, z alpha by 2, that is equal to 0.01, and that is equal to 0.99 or 0.9900. You can find this value in the table, and that corresponds to 2.33. 2.3 and 3 on the horizontal line. So 2.33. And I would like to plug this value in my formula x bar minus, you know, this thing that is equal to z alpha by 2 and sigma over square root of n is less than nu is less than x bar plus z alpha by 2 and sigma over square root of n. I don't want to write all this formula again and again. So it is 174.5 minus z alpha by 2 is 2.33 and sigma is equal to 6.9 divided by square root of n. So square root of 15 is less than nu is less than 174.5 plus 2.33 and 6.9 divided by square root of 50. Square root of 50. And if you plug the values, you're going to get, or use your calculator, and you're going to get that is equal to 172.23 is less than nu is less than 176.77. So this is my confidence interval. And this is my part A, and my part B says that my estimation, you know that E here is not, it should not exceed that one, right? So I'm not going to write equality, but I'm going to write less than, and z alpha by 2 and sigma and square root of n and square, if I'm not wrong, right? So E z alpha by 2, let me just make sure E is equal to of z alpha by 2, n equal to n, square is there for n. So this is E equal to z alpha by 2 sigma. Okay, that is square root of n. So let me just plug the values over here. That is equal to z alpha by 2, that is equal to 2.33. 2.33 sigma is equal to 6.9 and square root of n, that is equal to square root of 50. If you use your calculator, you will get that is equal to 2.27, and that must be the answer. So that's how you can solve the example. And now let me go for the last part. Let me save this one. So this file has been saved over here. And now I would like to go for, let me clear this picture. And now let's share my book. And my book says the last example, that is example 9.5 and 9.15. We are going to read this, both the examples simultaneously, 9.5 and 9.15. 9.5 says that a random sample of 100 automobile owners in the state of Virginia shows that an automobile is driven on average 23,500 kilometers per year with a standard deviation of 3,900 kilometers. Assume the distribution of measurements to be approximately normal. Construct a 99% confidence interval for the average number of kilometers an automobile is driven, 99%, okay? And what can we assert with 99% confidence about the possible size of our error if we estimate the average number of kilometers driven by car owner is in Virginia to be 23,500 kilometers per year. Okay, so it's just exactly same as your previous example, but additionally we have one thing over here that says that referring to exercise 9.5, construct 99% prediction interval for the kilometers traveled annually by an automobile owner in Virginia. I have one problem over here, guys. Here you are given n equal to 100, n equal to 100. But if you look at table A3, I think you will not find the value for n equal to 100, if I'm sure. Table A3 and right, guys, something like this. This is, but I think in this one, this is the example in which we are given 99% of the confidence interval. 99% of the confidence interval. And example 95 says construct 99% prediction interval for the kilometers traveled annually by the automobile owner in Virginia. That means in the second part, if I'm not wrong, in the second part, value of sigma, we cannot use. We are not supposed to use that value of sigma, right? Value of sigma, we are not supposed to use over here. But that sigma, that is a sample mean. Referring exercise 9.5, construct 99% of the interval of the kilometers traveled annually by an automobile owner in Virginia. That's the thing, that the things given to you. So I'm not going to take this sigma is equal to, of course, you can solve this example with here with n equal to 100, but here we have to use t distribution. And if you look at your t distribution, means table A4, last values are 60, then immediately 120, and then infinity. There is no 100. So guys, please make sure. So that's why I think something is wrong in the book. Something is wrong in this example. Otherwise, they have changed this value. You can write somewhere over here 50, 60, something like that, so that we can have all other values, but not like this, not 100. Okay, so here I'm going to solve this example by 100, but here I will change this n equal to 100. Instead of 100, I'm going to take 60, right? So the 60 minus 1, that is 59 or something, or 61, we can say. So n minus 1 degree of freedom for t distribution we can use over here for this one. So please this thing in mind that I'm not going to use n equal to 100, but I'm going to use n equal to 61 over here, just for the sake of convenience, because t distribution table, that value is not provided. That's the reason, guys. So take t equal to 61 over here. Very important thing. Yeah, it's an error in the book. This type of errors are not allowed. But anyway, book is good. Okay, stop sharing and let me go back to my whiteboard for the last example. Last example says that example 9.5 A and B part, first of all. So example 9.5, here my n is equal to 100. My x bar is equal to 23,500. My sigma, which will be S in my example 15. So here it is 39. And I am given 99%. You know this thing because so many times we did this thing, 99%, that is equal to 0.99, and that is equal to 1 minus 0.99, that is equal to 0.01, and divided by 2, that is equal to alpha by 2. So alpha is equal to 0.005, and that means 1 minus 0.005, that is equal to 0.995. So if you find this value, that value corresponds in table A3. Table A3, that value corresponds to 2.575. So Z alpha by 2 is equal to Z 0.005, that is equal to 2.575. Right, guys? 2.575. And now, using this information, I'm going to answer my question A. So A part says that, what is A? Let me put some lines like this. So A part says that 99%. Okay. So 23, that is my x bar minus Z alpha by 2. So 2.575. And sigma is equal to 3900 divided by 100. Square root of 100 means 10. Is less than new, is less than 23,500 plus 2.575 and 3,900 divided by 10. If you use your calculator, you're going to get something like this. Here 22,496 is less than new, is less than 24,504. That's the interval. And my B part says that my error estimation should not exceed. So E is less than Z alpha by 2 and sigma divided by square root of n. Z alpha by 2, that is equal to 2.575. Sigma is nothing but 3,900 divided by 10. So that is equal to 1004. So that is my A and B parts. That is my example 9.5. And now I would like to go for my example 9.15. So in the continuation, I would like to go for 9.15, but with n equal to, suppose 61, n equal to 61, okay? So if I say like this, n equal to 61, and my x bar, now it's not sigma, x bar equal to 23,500, and, x bar equal to, and my not sigma, but my s is equal to 3,900, and 99% of the interval. So 99% will remain exactly same thing over here. 99%, that is this one. That is this one, right? But 99%, that is equal to 0.99. So 1 minus 0.99, that is equal to 0.01. That is equal to my value alpha. Alpha by 2 equal to 0.005. So T 0.005. So T alpha by 2, t is 0.005, that is equal to my degree of freedom, v equal to n minus 1, that is equal to 61 minus 1, that is equal to 60. So v equal to 60, v equal to 60. And 0.005, that is my value of alpha in t distributions on the horizontal line, and that corresponds to 2.66. That corresponds to 2.66. So use this value 2.66 in the degree of freedom, and now I'm going to write that is equal to x bar minus t alpha by 2 and s over square root of n is less than mu is less than here sigma unknown. Sigma unknown is less than x bar plus t alpha by 2 and s over square root of n. Just plug the values you're going to get, that is equal to 23,500 minus 2.66 and s equal to 3,900 by 10 is less than mu is less than 23,500 plus 2.66 and 3,900 by 10. If you use your calculator, if am I right, guys? I think values are a little bit different, right? Plus or minus t and sigma, and then it is, what is the definition? 1 plus 1 over n, right? That is the definition, guys. So I think I made little mistake over here. So let me, no. Let me do this thing. Let me just remove this part. Okay, this is actually eraser, and let me erase this part and let me erase this part. But actually, it is nothing but you have this one, and then sigma. Sigma is equal to 3900 and square root of 1 plus 1 over n, right? So sigma square root of 1 plus 1 over n, and n equal to 100. So you can n equal to 100 or n equal to 61. What is given to us? N equal to 61. Okay, so n equal to 61. Just plug this value. So 2 here 3900 and square root of 1 plus 1 over 61. And whatever the numbers you are getting, one number you are going to get from here is less than mu is less than, my second number is over here. So that is your confidence interval. So that's how it works, guys. So please try to make sure about this thing and try to work accordingly. Thank you so much, guys. And I think this is the end of article 9.1 to 9.5, only 9.1 to 9.5. Next time we are going to start 9.8. Thank you so much, guys. Let me stop over here. So again, it's a long video. Yes, and let me just stop sharing this one.